Well, thanks for giving me the opportunity to talk here. I'm very happy that my talk is following the previous one because Jake talked about containerization, so I think it's a nice sequel. Oops, go back. So this is work with. I still want to see the title page yet. So this is work with Andrew Pauling from the University of Otago. I'm not sure why it's. Can we? Yeah. Dini from NeSI, Chris Scott from NeSI as well. And this was part of a consultancy service that we offer. So if you have any interesting project or problems that you want to solve and you need a little bit of help from research software engineers, then please talk to us. So the first thing that you're going to learn today is what containerization is and how to leverage containerization in a research computing environment. And perhaps also some gotchas, some traps and some things that are sometimes a little bit unexpected. So what is containerization? Well, what we found is that researchers tend to, as in the case of Quake Core, they have to assemble, complicated, complex simulations, and these simulations are made of executables that have to be compiled, and they depend on libraries, and the libraries have other dependencies. At the end of the day, they may depend on a particular compiler, and that compiler might actually depend on a different, certain environment, Unix or Linux, and it's sometimes challenging to assemble all these blocks. And we know that for sure because a couple of years ago, I think we had an upgrade on MAUI, which is one of our platform. And we thought that by changing a couple of libraries at the back end, we wouldn't impact the users, but it was very much the opposite. And at one point, I had a colleague back at NIWA, and we had a discussion, and I could really see my colleague getting really frustrated about having to recompile the tool chain and the code and spending essentially months to do that particular job. So containerization is really here something that should potentially help you. Because all these different blocks, NetCDF, MPI, I don't have to go into the details of those libraries, but they depend on each other and they don't always fit neatly with each other. So finding a build process that can be carried over to a new platform as is can be very beneficial. So containerization is really something that bundles the application with all its dependencies. So why would you need to use containerization? One scenario is that right now MAUI is getting quite old, and we think about turning it off at some point in the future. We don't know exactly when that's going to happen, but there are some changes going on. MAUI is going to be reverted to NIWA. That's one thing. So that's a certain deadline. And if you have code that is currently running on MAUI, then you'd have to port that to a different platform. But why not making it in such a way that it's portable to any other platform or most other platforms? Then that could be useful. Maybe you need reproducibility. You're writing a paper, and 5 years later, people come back to you and ask you to rerun a simulation, and you no longer have access to that particular environment. So maybe you're going to get different numbers just because compiler versions have changed and the versions of some libraries have changed. Or maybe you have to debug, or maybe you want to share your executable. So that's a good test case. You're working with some colleagues in the US or in other countries, and you're running your simulation, and you can just say, hey, here, why don't you use that container, and you should get exactly the same numbers. Or maybe you have to debug a problem, so somebody sees a problem in a certain environment, or and that's the case also with a recent sort of work we're doing with Wolfgang, who is also present here in the room, but where we're trying essentially the latest bleeding version, edge versions of a compiler on some particular code. And so it's quite easy to create a new container, and requires much less intervention. You don't have to send an email and wait for somebody to install the software. You can just do it yourself. So as a motivation, I'm just repeating it, but if you are currently running on MAUI, then think about porting your code to our Milan nodes, and that should help you get going on the future Genoa nodes that we're in the process of installing. And also, we want your software to be fair. That means findable, accessible, interoperable, and reusable. And containers help you achieve that. So what are the options if you want to port your code? Well, you can always build a static executable, and that could work on a number of Linux platforms, but you have to be careful how to do that. You could also have a flexible build system that doesn't care so much about the OS, the operating system, and its environment. You could have a conda recipe. Yeah, well, that could work, but it's not always well optimized for a given platform, and you can have some licensing issues. You could use SPAC, and SPAC is very promising. I've been convinced by Wolfgang, for instance, how useful that is. And that's maybe a technology that would be worthwhile mentioning at an eResearch conference. Alternatively, you have also Docker, which is a containerization technology, but it's not really designed to be high performance, to run on high performance computing facilities. And so what Aptena does, it basically can take a Docker container and make it run on a high-performance computing platform as is. So it supports Docker images, and so you can develop in Docker and actually run in Aptena. So how do Aptena containers work? Well, Aptena used to be called Singularity. There's the open source sort of version of the free version is now called Aptena. But it's essentially just a recipe, and just like Jake said, it's also a file that you can hand over to somebody, and it's a binary, and it can be shared, and it comes, with operating systems, libraries, compilers, whatever you want to add to that particular container. So it's good to remember that a container is just software at the end of the day. While a container may come with MPI, message passing interface, and it cannot possibly know about the communication fabric that you have on your high performance computing platform. So there will be some things that will be absent, and I tend to regard the container as being a car without the wheels. So you can sort of hand over the car, but you still have to attach the wheels. The wheels essentially are the things that connect you to the ground, to the road, and without the wheels, you can't drive anywhere. So how do you run? If somebody gives you a container, how do you run your executable that was compiled inside the container? Well, all you have to do is just Aptena exec the container file, which is called CIF here, and then the executable, which is defined inside the container, and maybe some options if it takes some options. One of the things that you will notice is that there's no module load or none of that stuff. So it's also simpler to run in some sense an Aptena executable. Now on NeSI, what we would recommend is actually do a module purge, because really you don't need any modules apart from Aptena to be loaded. And then once you have that, then you can just run. Occasionally you might have to bind, what is called binding, basically bringing in external directories into the container for the executable to be able to actually access, input data, or maybe write the output data there. So that's a -B option. And sometimes, if you have an Aptena that is executable that should run on a GPU, then you might have to, you will have to actually provide the --NV option for NVIDIA types of GPU. I'm not sure if it would run on other types of GPUs. And now for an MPI code, it's a little bit more tricky. There are really two possibilities. You could run the code in parallel inside the container, but usually we sort of limit it to a single node in that particular case. Again, because the MPI inside, doesn't really know about the MPI outside and thinks that it's all shared memory. Or you could actually use the MPI on the host under some conditions, but the MPI inside the container version, has to sort of map or match roughly the MPI outside. So that works as well. And that in itself can, and then after that you can use the srun command as you would normally. So srun inside you slurm script, Aptainer exec in the usual way. So the use case here is the New Zealand's Earth system model. So we worked with Andrew Pauling on that, and that's a big application, lots of dependencies, tools, and there's a Silk version, an older version, 7, Silk outside, which is 8, and so it brings a lot of complexity, and that was of course the reason why the researcher I mentioned, felt so much grief after a small change in our environment. And so, there's an ocean model, there's an atmospheric model, developed, a UK Met Office, and so we had to deal essentially with all that. And the result of that is that the researcher now, it was running on Maui, can now run on Mahuika or on the Milan nodes of Mahuika. It doesn't matter, either way or another. So you have more choices, essentially, to run the application. When we say Mahuika, we basically just mean the Aptainer version of the particular code, and is happy with the results, which have some differences. But the researcher said that he sort of expected some of the differences just because of the nature of the partial differential equations that are solved, which tend to be nonlinear. So after some time, you accumulate differences, as is often the case in climate modeling. We had in the past, previously, we had another team also working in earth sciences, and they did sort of ice sheath simulations, and we worked with them and got them essentially running on Mahuika. So in summary, I think it's possible to write supercomputing applications that run anywhere, with some caveats, which I'm going to mention briefly. But containerization is also a way to replace the module system that you might have in your environment, which is very powerful but a little bit delicate occasionally. You can build the containers on your laptop, so that's really a nice feature. So I tend to develop on the laptop and then run everything on the supercomputing platform. So it's easier. You don't spend time going through a firewall, connecting SSH and all that. You still need to run on the same type of architecture. So once you build your container, let's say on an Intel platform, then it will have to run on an Intel platform. It won't run on an ARM platform. And that means that occasionally there could be some issues if you were to build on Intel and use some compiler switches that are specific to Intel, then the application would actually refuse to run on non-Intel hardware such as AMD. And please check out NeSI's case studies where we containerized scientific code. And always happy to talk to you if you have any questions, when you think that we could be helpful. I think that very happy to have a chat with you. That's it. Thank you.
Did anyone have any questions for Alex?
Hi. So just on that last point there about supporting the containers on NeSI, what do you think that, as a replacement for a module system, what do you think that NeSI could do to make that easier for people? Because at least to my understanding, the uptake of containers is not that high at the moment in HPC environments.
Yeah, so the question is about the uptake of Aptena technology within NeSI, which could be higher. I mean, there's a certain complexity associated with that. You have to learn, a few commands, how to build the Aptena, how to run, and of course, we still have to build the application on the particular platform. So that's an impediment, and maybe I'm not saying that Aptena would necessarily be the solution for to all the challenges of porting these applications. SPAC could also be another option, but on the plus side, it is a recipe, and I think what we've seen very often in the past is that the researchers would tell us, oh, you do this, you do that, and they're sort of a little bit vague about how what commands have to be typed and in which conditions, and that's also a big source of grief because very often it doesn't quite work this way, and we have to get back and have emails, and with a system like a technology like Aptena or SPAC and so forth, it's a clear recipe. You can just either execute the file or copy paste the 3 or 4 lines of SPAC and you should get exactly that result. I hope I understood. I answered your question. Yeah. Chris?
Sorry.
Yeah.
Hi.
Calculus.
Hey. So early on you mentioned that Docker isn't ideal for HPC. Coming from tech, I've seen just Docker used everywhere, kind of exclusively. So could you offer a little bit more information, some basics of why it doesn't?
Well, it assumes that you have root access. So basically, we typically don't. I think most supercomputing centers do not allow essentially Docker to be run directly. So so I guess that's the main impediment. So Docker would work really well if, but there's that sort of root access issue.
Yeah, we'll talk more about it later.
Yeah.
Thanks, Alex. Great talk. I have a couple of comments very quickly and then a question.
Sure.
First comment, MAUI is reaching end of life. So that's why people have to move on, right?
Yeah.
Second comment, I think Conda and SPAC are great additions to containerization because it avoids having to build each and every package by hand as in a script that you have to put into your container recipe, and then you have a container recipe that's 200 lines long or so because you have to go through, 30 different packages that you need to build. My question is, when do you think is containerization not a good idea? Because there are some obvious overheads that you have to do, right? So if you make a change, you rebuild your container and so forth. So can you think of examples where you would not recommend it?
That's a really good question. Thanks, Wolfgang. Except for the gotchas, with the sort of the MPI issues potentially, or if you have to run on GPUs, then you just have to be a little bit careful, but it should work. So perhaps if you have to run on AMD GPUs, for instance, I don't have any experience with that, and that might actually not work. Or if you using maybe an MPI library that is which is not really supported, is maybe not one of the main ones or something, then it might be difficult to have that MPI version on the host and be able to run on multiple nodes. These are the reasons I can think of. Chris?
Following Wolfgang's example, I've got a comment and a question. Well, the comment's actually good news. So the thing about the MPI, the compatibility between the MPI libraries, that will hopefully be going away soon with the newest version of MPI. They're proposing standardizing the ABI.
application binary interface.
So those will be compatible.
Yeah.
The question is about your advice to avoid host-specific optimizations.
Yeah.
So that you can build a container that's portable across different generations of the hosts. That would seem to be in conflict with the desire to have green HPC. So this might not matter if you're containerizing LS or you're containerizing CAT, but if you're containerizing an Earth system model, which you'd expect to run for hours or days on end.
Yeah, it's a trade-off. I mean, I totally agree. I mean, sometimes you might have an application where a 2 or 3% increase in performance is really critical, and you may forego some of the portability in order to get that increased performance. That's really a call for people to make. I think what is important is just to be aware that. That if you're just compiling on one platform, another platform may not actually support that particular instruction set. But absolutely, yeah.
Is there any other questions from anyone? Yeah, you do. We've got 5 minutes, so go for it.
Great talk, very interesting. I was just wondering, in terms of creating containers that basically you could reuse, did you have any lessons learned about when you configured the container? So I've tried to do reproducible builds in the past, and one of the lessons I learned was not to pull latest, to pull a specific version of the container you're going to use, install specific Python versions, stuff like that. I was wondering if there were anything like that you can kind of share with us.
Yeah, I mean it really depends on the applications. I mean, sometimes the application really wants, an older software stack, an old set of compilers, and then you really don't want to use the latest. I tend to go for the latest if that works, but sometimes we have to unroll things back in time until we get something working. Just because the application by itself may not be super portable. That's a little bit my opinion. We can have another discussion, afterwards. Yeah.